Hello everyone, welcome back to my channel. In the last video, we have built an MNIST classification model from scratch using only NumPy. We did not use TensorFlow or PyTorch over there. In this video, we will solve the same problem using TensorFlow 2.x. I will show you the previous code also what we have already done in the previous video, and I will show you how easy it is to do the same thing using TensorFlow or PyTorch repositories. In this video, we will stick with TensorFlow. The whole implementation, the architecture implementation, forward pass, backward pass, all of those things you can actually implement in few lines in TensorFlow. I have already loaded my Google Drive here. Now let's start the project. So first I'll import the necessary libraries. So import TensorFlow as TF, and then I will import matplotlib for plotting the images, and I will import NumPy. So I think these three libraries are good enough. Let's see if we need anything as we go through the code, we will import those. So before going further, first check the TensorFlow version. So this is TensorFlow 2.8.2 version, but this particular code should work with any 2. Version. Even if it is 2.0 or 2.1, any version it should work. Now let us load the dataset. In our previous video, we have shown the dataset loading from scratch. We have actually downloaded the dataset from Yanluken website, and from there we have converted the ubyte files into CSV file, and then we have visualized them. Then we have used the network for training. Now, one good thing about TensorFlow or PyTorch or Scikit-learn, these kind of frameworks is the datasets are also available as part of the framework. So if I want to load the dataset now, the same MNIST dataset, I need not to worry about loading the files, reading the files, getting the labels as well as the images, all of those things. I can directly load them into the images and label variables directly from the TensorFlow. Actually, TensorFlow has Keras as part of it from 2.0 version officially, and inside Keras we already have MNIST dataset. So I will just need to load data. That's it. Now this MNIST dataset I need to take into some variables. So by default this MNIST dataset has both training as well as testing data. So first I will take one tuple of two variables, which is xtrain and ytrain, and then I will take the test variables xtest comma ytest. So this is how you can load the MNIST dataset directly from the TensorFlow. So it is giving us directly the training data as well as test data. And also it is giving the images and labels separately. So let us load it. It will download it now into your local. Yeah, it is done. The training data has actually 60,000 images and the test data has 10k images. So let's print the shapes of these. So this will print the shapes of input images as well as the labels for both training and testing. So if you see the xtrain, the first one is input images. Input images are 60,000 images and each image of 28 by 28 pixels. At the same time, test images are 10,000 images with 28 by 28 pixels, and the corresponding labels. The training labels are 60,000 and testing labels are 10,000. Now we will just visualize the image. So first I will just print the image first. Let's suppose I am printing the 100th element. That means the 100th image. If I print this image, you can see that the values are ranging from 0 to 255 because it's a single channel grayscale image. Okay, now let us plot the image. So I'm just plotting xtrain of 100. So let's see how it looks like. Which digit is it? Along with this, I'll print the label also so that we will know whether the data is proper or not. So this one label is actually ytrain because I'm taking from the training dataset. So now let's see what it gives. Okay, so you can see this is an image of 5. If you remember the same thing we have printed in the previous video also, 100th image, which is 5 and the label is 5. So our data is fine. Now we need to actually normalize this data set. So normalizing is very simple. You just need to divide by 255. So I'll just divide the train images with the 255. Same thing I will do for test images. So now these are normalized. That means the values are ranging from 0 to 1. So now the values should be between 0 and 1. So you can see all the values are in the range of 0 and 1. Okay. So we have normalized the input dataset. Now we have actually loaded the dataset. We have visualized it. It is fine. Now let's build the network. So if you remember in our previous video, we have used this network. So the input is actually dense layer with the 784 nodes. This is input layer because we have 28 by 28, and then two hidden layers 128 64. So for building that network we wrote all these things: initialization, getting the sizes, and then initializing the weight parameters randomly. After that, activation functions, whatever we are using, forward pass here and then backward pass here, and updating the weights, computing the accuracy for evaluation. So all of these things we have written, even the training loop, all of these things we have written ourselves. Now let us do the same thing using TensorFlow and see how easy it is. Okay, so in TensorFlow there are many ways of building the model. Just to show you the similarity to the previous thing which we have done using NumPy, I will use the class method. So we can actually use class method in TensorFlow to build our models. This is one of the best way to build the models. When you are actually building the model in TensorFlow, you need to inherit that class from the TF Keras model. So why we are doing this? Because if we do this inheritance, then automatically the TensorFlow will take care of the backward pass. We need not to write the backward pass in this case. So I'll just do init function and then we need to go to the super class. Once we are done with the super class, let's suppose I am keeping pass for now. Okay, this is my initialization, the same as what we have done in NumPy. Even in NumPy, we need initialization. So where my parameters and layer weight values, all those are initialized here. The same way we have just kept one initialization. We will fill those details later. Now the forward pass we need. For forward pass, we will directly use the call function. So the call function is actually available in Keras model class and we will actually overwrite it here. Consider this as forward pass. And we need not to write any backward pass function here because TensorFlow takes care of the backward pass function. And even for computing the accuracy, we don't need any function because this Keras model has all the functions available. We can directly use those functions when we are training and evaluating. So we need only two functions here. And for this function, like we have done previously, we will take sizes as the input. So I'm just initializing my model is equal to DNN of sizes. Sizes I will give 128, which is my hidden layer, first hidden layer, 64, second hidden layer, and 10 output layer. So the input layer, I am not giving any dimensions because my images I am getting 28 by 28. I can directly convert them into a single 1D array and then pass to the network directly. So I need not to mention anything here. Okay. So this is the one I am calling. So now sizes, if you see, I am getting three values. So I'll directly take self dot hidden one. So 128 self dot hidden 2. Sorry, I need to take from sizes of 0, sizes of 1, and self dot output layer size. I will directly take sizes of 2. So these are my dimensions of each and every layer. Now I need to build the layers here. What are the layers I need? First layer is my input layer. So what is the input we are getting here? So the input image shape is 28 by 28. But our network is fully connected network or dense network. So it accepts only 1D array. So for that, the 28 by 28, we need to convert it into a single 1D array. For that, we have flatten layer available in TensorFlow. So I will directly use tf.keras.layers. So whatever the layers you want to use, like the dense layer, which is your fully connected layer, or flatten layer, or any activation layer, every layer is part of this tf keras layers. Okay. So in this one, I'm using flatten layer. So flatten layer, I will directly give input shape. I'm just mentioning, okay, this is a flatten layer. The input it will get is 28 by 28. And what it needs to do, it needs to take this 28 by 28 input and convert into a single flattened 1D array. So that's what this layer will do. That is fine. And then we will actually do hidden layer 1. Hidden layer 1 is actually dense layer. So in TensorFlow, we call it as dense layer. So even though it's fully connected layer or dense layer, both are common names. So we call this as dense layer. And in dense layer, what is the dimension? Self dot hidden one. These are the number of neurons available in dense layer. And if you remember, we have written a separate function for sigmoid activation function. But here in TensorFlow, you can directly mention just the name. Activation is equal to sigmoid. That's it. You need not to implement anything. So now this dense layer, it has a fully connected layer followed by sigmoid activation function. Same thing I'll just replicate for second hidden layer. So I just need to modify here hidden 2 and hidden layer 2. And I can actually use the same thing for output layer also. But in output layer, if you remember, it is a multi-class classification. We can use softmax activation. And here the dimensions are output layer size. And then this one I can keep output layer. The name as output layer. Okay. So if you see here, what we are doing in the initialization, we are only writing the building blocks. So as of now, there is no connection here. In the initialization, there is no connection. These are only layer initializations. Only the layers with the corresponding number of nodes will be initialized with random weights. As of now, the network is not yet connected. It has only built the building blocks. So let's suppose that I'm getting X train here, right? So this is my input I am getting here. Now this input, it has to go to the input layer first, right? So I'm just keeping X is equal to self dot input layer of X train. So whatever X train I'm getting from the actual data 28 by 28, it is passing through this input layer, which is my flatten layer, which will automatically convert these 28 by 28 into 784 numbers, and it will give the output here. Fine. Now this output I need to pass to my first hidden layer 1. Okay. So if you see, I'm actually connecting the network now. So whatever the output I am getting previously, that I am giving as input to my second layer. And now whatever the output I am getting from the second layer, I need to pass that as input to my second hidden layer. That means third layer, layer 2. If you see, it's just like a simple function call, all the connections. So one output is going as input to the next layer. So the same way, my final layer is actually output layer of X. Okay. So now X is my final output. So this is the network. That's it. So the whole network we have built in just hardly like 10 lines, right? If you see here, we are just building the necessary components here in the initiate function. And after that, we are writing a call function, which is a forward pass function. And then we are connecting the network here. That's it. So now I'll just run this part and then run this one. Okay, DLN has no attribute self. Okay, sorry. Okay, so now I have data loaded and the model also built. Now what I need to do is I need to identify what is the loss function I want to use. I need to identify what is the optimizer I want to use. Okay, there are different optimizers available. In our previous video, we did not see any of those. We made it very simple. We just take a simple subtraction as a loss function and we did not use any optimizer or anything. Only learning rate we have used. Now here I'm actually initializing one optimizer. So for keeping the optimizer and the loss values, all of those things, we need to compile the model. So there is a function available in the Keras models, which is compile function. So for this function, we can mention what is the optimizer. Okay, so for optimizer there are so many things like SGD, Adam, all those things. Okay, as of now I'm using Adam here. Fine. Then loss, which loss function I want to use. So I want to use sparse categorical cross entropy. So I'll just use sparse categorical cross entropy. Okay, and then along with the loss I want to calculate the accuracy also, and I want to see the accuracy also in the log values while training. So for that I can just keep metrics is equal to accuracy. So if you remember, when we are training on our own using only NumPy, we actually calculated the accuracy. We wrote a separate function for calculating the accuracy and we printed the accuracy during training. But when you are using this TensorFlow like this, you can directly mention which value you want to print during training. So I want to see the accuracy. If you want to see the precision or you want to see this one, some F1 score like that, you can mention those values also here. At the same time, for the previous video, we used a simple difference as the error, but here I am using a proper loss function. So it is actually log loss. So both will work, but this one logarithmic loss is better suited for classification problems. So you can actually see the difference in accuracies also. So for now, I am using this compile function for adding the optimizer details and loss function and the metrics. Now my model has compiled. Now I need to train the model. So for training the model, you need not to write a for loop for loading one by one image and feeding to the model. So there is a function called fit in Keras. Directly you can use the function. All you need to pass is your input images and your labels. And how many epochs you need to run here? let's suppose I want to run 10 epochs. You just mention that. That's it. And then you start training. So it will start training. So you can see this loss value, accuracy values. Okay. So you can see we are starting with the accuracy of 0.87. Okay. If we have used earlier, which we are actually using the simple difference, while training, what was the loss we are getting? Accuracy we are getting 25%, right? After 10 epochs, we are getting 56% accuracy. That is because we did not use any kind of optimizer. We are just using the LR value. And the second thing is the loss value. So loss, we are directly using the MAE loss. We are not considering the logarithmic loss, which is better for classification. So here we are considering the categorical cross entropy loss, which is logarithmic loss. So that is actually best suited for classification. So that's why you can see the accuracy, loss values are decreasing, accuracy is increasing from the beginning. So we have completed all the 10 epochs. You can see the accuracy, the final accuracy is 99.28 percentage. So now actually I need to evaluate my model on the test dataset. So even for that, we have actually model evaluate. So there is a function directly available, which is evaluate function. So I can directly give x test and y test, my test data, and it will give me loss and accuracy. So what is the test loss and what is the accuracy? Now I'll just print the accuracy here. So now it will actually test our model on the whole test data set, and then it printed the accuracy. So you can see the test accuracy is 98%, almost 98%. So now actually this accuracy is a good measure for the total model, but I want to understand how my model is performing on each and every label. So this is a multi-class classification which has 10 classes. I want to identify if my model is performing good on all the classes, right? So for that, the best thing we do is print the confusion matrix. So I'm assuming you already know the confusion matrix. Now we'll print the confusion matrix. So for printing that, first I will actually take the predictions from the model. So actually the model is classification model, so it will give the probability scores. So I'll just use predict function, which is available as part of TensorFlow, and I will give test dataset as the input. Now this will predict and the whole test dataset, and it will give me the probability scores for each and every image. Now I don't need the probability scores. I need the actual label, right? So labels are actually wherever the highest probability score is there, that particular index I will take. So I'm using argmax, numpy argmax, because I need the index value. Argmax actually gives the index value for I in ypred. So now if I print, I should get actual labels. I should not get probability scores. Okay. So if you see this, all these are, that means the first image is 7. Second image is of label 2. Third image is of label 1, like this. So on my test dataset. Now I have the similar kind of data on y test. Y test is actually having the same data for me. That is actually the ground truth. So if you print the y test, right? So if you see, this is actually giving the similar data. So it is having 10,000 images. This also will have 10,000 data. Okay. Now these two I need for getting the confusion matrix. So let's suppose I'm taking confusion matrix is equal to tf.math dot. So it is already available as a function in TensorFlow. So I can directly use math confusion matrix. And first I need to give the ground truth, and next I need to give my network predictions labels. So now if I print confusion matrix, let's see how it is performing on each and every class. Yeah, so you can see this. So the first class 971, all other, these are all false positives. 1120 false positives. 11. So if you see whatever the false positives and false negatives, those are very less number compared to the actual correct predictions. So these diagonal values are my correct predictions. So because if you consider the columns are ground truth and the rows as predictions, it will be like 0 0 label matching, 1 1 label matching, like this. If you consider the first one, that indicates my ground truth is 0 and prediction is 0, like this. Okay, so that way you need to interpret the confusion matrix. So if you observe, I did not see bad prediction on any of the label, all the labels, that means all the classes it is performing good. Okay, now this is fine. Okay, this is very smaller data set, maybe you have trained in couple of minutes and then you are testing it, it's fine. But if you got very big data sets, right, the training will go for hours. You cannot keep this waiting till the training is completed and all those things are done. So for that, now whatever the learnings are happening, all those things are available as part of this model variable, right? This model variable has all the layer weight values which are learned now during this training. Now I don't want to lose that. Suppose if any, because of some error, this training got crashed. So I had to close this collab. Now all my weights are gone, right? To avoid that, I want to save these weights. So for that, there is a function available, save weights. Okay. Now I want to save the weights in my Google Drive. So I'll just open this. So in my drive, there is an MNIST folder. So I want to save the weights here. Okay. So directly you need to give the path till the model file name, dense model.h5. So h5 is the file name for the weight values in Keras. Okay. So now it has saved. Now if I see this MNIST folder, so it has this dense model.h5. So these are the weight values of my model. Now even if I lose track of this total training process also, I can directly load my model. So just to show you that, I'm deleting this model variable. Okay. Now my model does not exist. Whatever the training weights I have actually trained, all those are gone. Now good that I have actually saved it as a model file here. Now how will I actually take this back and then use it further? So I'll just copy that model initialization. So this is one. So I'm just initializing the model again from my class and then I'm compiling the model. So for evaluation and training, you need compilation. If you want to get only predictions, you don't need model compile. But for evaluating, getting the accuracy scores and all, you need to compile the model. So now we have actually loaded the model. Okay, now this model is actually having random weights because I have initialized it from scratch now, right? Just to show you that, I will just evaluate it. So let's calculate the loss and accuracy by using model.evaluate and print the accuracy. So accuracy, I am printing it here. So if my model has actually already learned model, it should give me 97% on the test accuracy. Now, as I was saying, this model is initialized from scratch now. So that is not a trained model. So the accuracy should be very less. Yeah, you can see the accuracy is 11%, right? So that means the model is initializing from scratch here. Now, how do I load these weights, which are my trained model, right? So for that, I need to write this model load weights. I need to give the path. So where it is located in this path. So I can directly load the weights like this. Okay. So now let's see. Okay. So I have loaded the weights now. Fine. Now let's calculate the accuracy again. The same thing I'll do just to show you the difference. Yeah, you can see 97.6%. So you see before loading the weights, it's 11 point. That means the model is not learned here. And after I loaded the weights which are learned here, then the accuracy is 97%. So like this, now I have trained the model here. I saved the weights here. I can say I can actually share these weights with someone else and he can actually load it in his machine like that. So even some trainings happens multiple days. For those things, it's better to save these weights at regular intervals because you will not lose the data. So yeah, that's all from this video. So this one we have done in TensorFlow. In the next video, we will do the same thing in PyTorch. PyTorch also follows the similar process. I'll just show you in the next video. Thank you.